Dear students, welcome back to e-class. Yesterday we discussed about module 4. In module 4 we will discuss about the introduction about the nanomaterials, as well scope of the nanomaterials and history of the nanomaterials, and one more uh, fabrication methods of nanomaterials also we discussed in the previous class. Today we will discuss detailedly about the synthesis of nanomaterials. The synthesis of nanomaterials is a design and preparation of the nanoparticles with a high functionality, that is to fabricate the nanomaterials which have the suitable properties for applications. The fabrication of nanomaterials of tailored properties involve the control of size, shape, structure, composition and purity of their constituents. There are two methods which we are going to fabricate the nanoparticles, different methods which are top down and bottom up approaches, and also we will use the growth kinetics, cluster formation followed by the nucleation and growth. Let us discuss the nanoparticle synthesis, top down approach and bottom up approach. There are two approaches for the synthesis of nanoparticles and the fabrication of nanostructure. As we can see, this is the top down. So in top down, initially the materials are in the bulk type, then they are turned into the powder. That powder is which are then fed into the synthesis process. Then you can get the nanopowders. The top down approach refers to the slicing or successive cutting of the bulk material to get into a desired shape of the particle. So coming to the bottom up approaches, dear students, initially the materials are in the atoms or molecular form, then they are clustered, then they are combined together to form a cluster, then that cluster is fed into the synthesis process. Finally we can get the solid nanoparticles powders. The bottom up approach refers to the build up of materials from the bottom, atom by atom or molecule by molecule. Atom by atom deposition leads to formation of the self assembly atoms or molecules and clusters. These clusters come together to form the self assembly, a monolayer on the surface of the substrate. Now category is based on the phase of the starting materials, top down approach. In top down technique, the starting materials in a solid state, as we can discuss earlier, which are also called as a physical processing methods. In this method, the mechanical methods, cutting, etching, grinding and ball milling. So grinding method we will discuss, we have discussed in previous class. uh, Lithography techniques, photolithography and electron beam lithography techniques, which are comes under the top down approaches. In bottom up approaches, dear students, all the bottom up techniques, the starting materials either a gaseous state or liquid state of matter, which are also called as a physical and chemical process methods. In physical techniques, the physical vapor deposition (PVD) involves the condensation of the vapor phases and evaporation, sputtering, plasma arching, and laser ablation. In chemical techniques, CVD deposition, vapor phase of reaction, and self-assembly monolayer, electrolyte decomposition, Solgel method, uh, microemission route, and pyrolysis methods. So how to synthesize the nanoparticles, dear students? The key to make a nanoparticles is how to control and stop the reaction to make a nano-sized product, because the properties of the nanoparticles depends on their size and morphology. The top down refers to the traditional workshop or micro fabrication method, where the tools are used to cut, mill and shape the materials into the desired shape and order. But bottom up refers to the methods where the device create the themselves by self assembly. Chemical synthesis is a good the example is that the build should be an example. The bottom up should broadly speaking able to produce the devices much cheaper than the top down method. So as you can see the image, dear students, this will indicated or shows the top down versus bottom up processes. Now coming to the advantages and disadvantages of the both the approach, top down approach. Coming to the top down approach, the advantage of the top down approach: the large scale production, deposition over a large substrate is possible. uh, Chemical purification is not required. So, Disadvantage of this top-down approach: the broad size distribution, the range from 10 to 1000 nanometer. uh, Varied the particle shape or geometry, control over the deposition parameters is difficult to achieve. The impurities, stress defects, and imperfection get introduced. Expensive technique. And coming to the bottom up approach, the advantage of the bottom up approach is that the ultra fine nanoparticles, nanoshells, nanotubes can be prepared. Deposition parameters can be controlled. Narrow size distribution is possible. The range from 1 to 20 nanometer. This is the cheaper technique. The disadvantages: a large scale production is difficult and a chemical purification of nanoparticles is required. Hope you understand, dear students. Dear students, welcome back to e-classes. Myself Santosh Vijay. Dear students, in previous session, uh, we have started a module 4, which is nanomaterials and characterization techniques. In that, we have discussed introduction part of the nanomaterials and characterization technique, and history and the scope of the nanomaterials we have discussed, and also we have discussed about benefits and applications of nanoparticles, and challenges and future prospects of nanomaterials. And finally, we have discussed bottom up and top down approaches to fabricate the nanoparticles. In that, uh, we have discussed one method, that is that is mechanical milling process. Today shall we discuss about the chemical synthesis techniques for the nano powders or nanomaterials. Dear students, let's begin this session with the chemical synthesis of nanoparticles. This is the bottom up approach, solution based processing routes used for the synthesizing the nanoparticles. Include precipitation of solids from supersaturated solutions, homogeneous liquid phase, chemical reduction, and ultrasonic decomposition of chemical precursors. These processes are attractive due to their simplicity, versatility, and availability of the low cost precursors. Uh, Inorganic salt compounds used in the wet chemical synthesis routes are more versatile and economical than the uh, other oxide employed in the sol gel process. A typical example of the formation of the nanocrystal is titania powder via hydrolysis of at lower temperature. Once the solution becomes saturated, the crystallization of the titania takes place either through homogeneous or heterogeneous nucleation. In the latter case, the crystal seeds are added to the solution to promote the crystallization of titania nanoparticles. A salt reduction is one of the most common adopted method to generate the metal colloidal particles. The process involving the dissolution of the metal salts in aqueous or non-aqueous environment, followed by the reduction of the metal uh, occasions to the zero valent state. The nature of the metal salts determines the kind of the reducing agent to be applied. The metal nanoparticles can also be generated via ultrasonic and thermal decomposition of metals. Salts are chemical uh, precursors. The power ultrasonic waves can stimulate the certain novel chemical processes due to the formation of localized hotspots in the liquid phase or extremely high temperature around about 3000 Kelvin, at high pressure around about 1000 atmospheric pressure. The main event in this process is the nucleation, growth, and collapse of the cavitation bubbles formed in the liquid. The cooling is achieved during the cavitation. Collapse is estimated to be greater than 2 into 10 raised to 9 Kelvin. This process is commonly referred to as the sonochemical method. The transition metal nanoparticles can be produced via sonication of their respective chemical precursors. For example, nickel has been sonicated under the organ atmosphere to obtain the amorphous nickel. The one disadvantages of this sonication process is that difficulty in controlling the resulting of particle size and distribution due to the agglomeration of particles into a porous coral like structure. A number of traditional and herbal methods of material processing could also possible lead to nanostructure formation. Hope you understand the how the chemical process is synthesis the nanoparticles. And now coming to the sol gel process, as we can see the image, dear students, this is the representation of sol gel process of synthesis of the nanoparticles. The sol gel process, which involves the evolution of the inorganic network through the formation of colloidal suspension, so called gel, and gelation of the sol to form the network in a continuous liquid phase, so called gel. uh, the precursors of the synthesizing these colloidal consist usually of metal or metalloid elements surrounded by the various reactive ligands. The starting material is processed to form the desirable oxides and form a sol in contact with the water or dilute acid. A removal of the liquid form of the sol yields the gel, and the sol gel transition is control the particle size and shape. The sol gel process refers to the hydrolysis and condensation of the oxide based precursors such as tetraethyl. The reaction involved in the sol gel chemistry based on the hydrolysis and condensation of the metals involved in the metal oxides can be described. The sol gel method of the synthesizing nanoparticles is a very popular amongst all chemical processes, is widely employed to prepare the oxide materials. The sol gel process can be characterized by a series of distinct steps, as you can see the image. The first step is the formation of different stable. This is the different this image here, students, the different solutions of alkali solvents, metal powders. The gelation results from the formation of an oxide or alcohol bridge network, which is called a sol gel. By the polycondensation reaction result in the dramatic increase in the viscosity of the solution. The third step is the aging of the gel. During the polycondensation reaction, the continue until the gel is transferred into the solid mass, accompanied by the construction of the gel network and the explosion of the solvent from the gel process. The aging process of the gel can exceed 7 days, and it is critical to the prevention of cracks in the gels that have been cast. The fourth step is dyeing of the gel is carried out when the water and other volatile liquids are removed from the gel network. This process is completed due to the fundamental changes in the structure of the gel. The drying process has itself been broken into four distinct steps. Number one is the constant rate period, critical point, and falling rate period, and the second falling rate period, which are the four steps. And the fifth method is dehydration occurs, during which surface bond groups are removed. These may stabilize the gel against the rehydration. This is normally achieved by the calcinating the monolith at a temperature up to the 8000 degrees Celsius. The sixth step is densification and decomposition of the gel at a high temperature around about 8000 degrees Celsius. The force of the gel network are collapsed, and remaining organic pieces are volatilized. Hope you understand the how the sol gel process is processed. Now coming to the one more method, that is the uh, Gas phase synthesis of nanoparticles. Dear students, the gas phase synthesis methods are increasing the interest because they allow the elegant way to control the process parameters in order to able to produce the size, shape and chemical composition controlled nanostructure. In a conventional chemical vapor deposition, the synthesis, the gaseous products either are allowed to react the homogeneously or heterogeneously depending on the particular application. In homogeneous CVD, particles form in the gas phase and diffuse towards to a cold surface due to the uh, thermodiffusion pores, and can either be scrapped of a formed and a cold surface to give the nanopowders or deposited onto the substrate to yield. In a heterogeneous CVD, the solid is formed on the substrate surface, which catalyzes the reaction, and thence the film is formed. In order to form the nanoparticles or nanomaterials, several modified CVD methods have been developed, and gas-phase process have inherent advantages, some of which are an excellent control size, shape and crystalline and chemical composition. Highly pure materials can be obtained. Multi-component systems are relatively easy to form. Easy control of the chemical reaction or chemical mechanisms. Most of the synthesis routes are based on the production of the small clusters, then can aggregate to form the nanoparticles. The condensation occurs only when the vapor is supersaturated, and in these processes or homogeneous nucleation in the gas phase, it is utilized to form the particles. This can be achieved both by the physical and chemical methods. We will take one example for this process, that is a furnace. As you can see, this is the as you can see this image, dear student, the schematic representation of a gas phase process of synthesis of a single phase nanoparticles from the heated crucible. This is the best example for the gas phase process. The nanoparticles are produced by the heating the desired materials in a heat resistance crucible. As we can see the image, the containing the desired material. This method is appropriate only for the material that have a high vapor pressure at the heated temperature that can be as high as 2000 degrees Celsius. Energy is normally introduced into the precursors by the arc heating, electron beam heating or Joule heating. The atoms are evaporated into an atmosphere which is either inert or reactive. To carry out the reactive synthesis, materials with very low vapor pressure have to be fed into the furnace in the form of suitable precursors such as organ metallics, which decompose in the furnace to produce condensable materials. The hot atoms of the evaporated matter lose the energy by collision with the atoms of the cold gas and undergo condensation into a small cluster via homogeneous nucleation. In case of a compound is being synthesized, these precursors react in the gas phase and form a compound which the material that is separately injected in the reaction chamber. The cluster would continue to grow if they remain in the supersaturated region. To control their size, they need to be rapidly removed from the supersaturated environment by a carrier gas. The cluster size and the distribution are controlled by one of these parameters: the rate of the evaporation, the rate of the condensation, the rate of the gas flow. Hope you understand, dear students, the gas phase process of synthesizing the nanoparticles. Now we will coming to the next method, that is the flame assist ultrasonic spray pyrolysis. As you can see the image, dear student, this is the flame assisted ultrasonic spray pyrolysis, which this process the precursors are nebulized, and then unwanted components are burnt in a flame to get the required materials. For example, zirconium oxide has been obtained by this method from precursors zirconium, CH3, CH2, and CH2O4. Flame hydrolysis, that is a variant of this process, is used to form the manufacture of the fused silica. In this process, the silicon tetrachloride is heated in an uh, oxyhydrogen flame to give a highly dispersed silica. The resulting white amorphous powder consists of the spherical particles with a size in the range of 7 to 40 nanometer. The combustion flame synthesis, in which the burning of the gas mixture, for example the acetylene and oxygen, or hydrogen or and oxygen, supplies the energy to initiate the pyrolysis of the precursors compounds, is widely used for the industrial production of powders in a large quantities, such as carbon black, fumed silica, and titanium oxide. However, since the gas pressure during the reaction is highly agglomerated, powders are produced, which is disadvantages of the subsequent processing. The basic idea of low pressure combustion flame synthesis is to extend the pressure range to the pressure used in the gas phase synthesis, and thus to reduce or avoid the agglomeration. The low pressure flames have been extremely used by uh, aerosol scientists to study the particle formation in the flame. A key for the formation of nanoparticles with a narrow size distribution is the exact control of the flame in order to obtain a flat flame front. Under these conditions, the thermal history, that is, the time and temperature of each particle formed, is identical, and narrow distribution result. However, due to the oxidative atmosphere in the flame, this synthesis the process is limited to the formation of oxides in the reactor zone. Hope you understand, dear students. Now coming to the gas condensation process. Next method to synthesis the nanopowder particles, dear students, that is the gas condensation processing. So as you can see the image, dear students, this is the schematic representation of typical setup of a gas condensation synthesis of nanoparticle, followed by the uh, consolidation in a mechanical press, or collection in an appropriate solvent media. In this technique, dear students, metallic or inorganic materials, for example sulfide, and vaporized using the thermal evaporation sources such as the crucible, electron beam evaporation devices, and uh, sputtering sources in an atmospheric pressure of 1 to 50 bar. uh, a cluster form in vicinity, as you can see the image, dear students. Cluster form in the vicinity of the source by the homogeneous nucleation in the gas phase, and grow by the coalescence and incorporation of atoms from the gas phase. Dear students, as you can see the image, the cluster of the particle size depends critically on the residence time of the particles in the growth system, and can be influenced by the gas pressure, the kind of the inert gas, that is helium or argon, or helium and argon, and on the evaporation vapor pressure of the evaporating materials. With increasing the gas pressure, the vapor pressure and mass of the inert gas used. The average particle size of the nanoparticles are increases. The long normal size distribution have been found experimentally and have been explained theoretically by the growth mechanisms of the particles. Even in a more complex process such as the low pressure combination film synthesis, where the number of chemical reactions are involved, the size distribution are determined to be uh, long normal. Originally a rotating cylindrical device cooled with the liquid nitrogen was employed for the particle collection. The nanoparticle size in the size range from the 2 to 20 nanometer are extracted from the gas flow by the uh, thermo phoretic process and deposited loosely on the surface of the collection devices as a power of the low density and no agglomeration. Subsequently, the nanoparticles are removed from the surface of the cylinder by means of a scraper into the form of metallic plate. In addition to this cold finger devices, several techniques known from the aerosol science have uh, now been implemented for the use in a gas condensation system uh, such as the corona discharge etc. These methods allow for the continuous operation of the collection device and other better suited for the large scale synthesis of the nanopowders. Dear students, now we'll move on to the chemical vapor condensation. As shown schematically in figure, dear students, the evaporative source used in GPS is replaced by hot wall reactor in the chemical vapor condensation or the CVC process. Depending on the hot pressing parameters, nucleation of a nanoparticle is observed during the chemical vapor decomposition, which is also called as a CVC of this film, and force a major problem in obtaining a good film qualities. The original idea of the novel CVC process, which is schematically as shown in the figure, where it was intended to adjust the parameter filled during the synthesis in order to suppress film formation and hence homogeneous nucleation of particles in the gas flow. It is rapidly found that the residence time of the precursors in the reactor determines if film or particles are formed. In a certain range of residence time, both the particles and film formation can be obtained. Adjusting the residence time of the precursor molecules by changing the gas flow rate, the pressure difference between the precursor delivery system and the main chamber occurs, then the temperature of the hot wall reactor result in the ferrite production of nano-sized particles of metals and ceramics instead of thin film as in CVD processing. In the simplest form of metal, organic precursor is introduced into the hot zone of the reactor using a mass flow controller. Besides, the increased quantities in this continuous process demonstrated that a wide range of ceramics including nitride and carbide can be synthesized. Additionally, the more complex oxides such as uh, beryllium titanium oxide or composite structure can be formed as well. Appropriate precursors compounds can be readily found in the CVD literature. The extension to a production of nanoparticles requires the determination of a modified parameter field in order to promote the particles formation instead of film formation. In addition to the formation of single phase nanoparticles by CVC of a single precursor, the reactor allows the synthesis of a mixture of nanoparticles of two phases or dropped nanoparticles by supplying a two precursors at the front end of the reactor and coated nanoparticles, that is zirconium oxide coated with the aluminum oxide or vice versa, by applying a second precursor at the second stage of the reactor. In this case, the nanoparticles which have been formed by homogeneous nucleation are coated by the heterogeneous nucleation in the second stage of the reactor. Because CVC processing is a continuous, the production of capabilities are much larger quantities in excess of 20 grams per hour have been rapidly produced with a small scale industry reactor. A further expansion can be uh, envisaged by simply enlarging the diameter of the hot wall reactor and the mass flow through the reactor. Hope you understand the uh, chemical vapor condensation process.